How are we doing, guys? Looking at installment savings here. So this is page 154, 155, questions 2, 4 and 8. The book has a section here on pensions and annuities, which I'm going to do a separate video on. So we'll only worry about installment savings in this video. Just to forewarn you, I have the calculations pre-done here on some of these questions, which means I'm just going to be producing numbers without the calculator. It's a bit faster. It saves you looking at the calculator. So questions 2, 4 and 8 is what I want to look at. Question 2 says Marie has saved €30 per month since her 18th birthday, and she deposits on the day of her 18th birthday, her first deposit, and that's important, that timing. Her bank has guaranteed her an interest rate of 4% per annum. Find the equivalent monthly rate of interest, correct to 2 places of decimals, and then find the values of her savings on her 21st birthday. So let's start off with, what is 4% per annum the same as what per month? That's a calculation we've seen before. We say 1.04, that's our yearly rate, needs to be the same as 1 plus r to the power of 12. That is our monthly rate, but that's done 12 times, and they need to be the same. So you take the 12th root, 1.04 to the power of 1/12 is 1 plus r, and then that's going to give us, that gives us 1.003273774. I'm going to take all of those decimals for that first calculation. But when you subtract 1 from both sides, you're left with 0.003273774 is the rate. They've asked correct 2 decimal places, so when you change that into a percentage, that's 0%, 0.33%. Okay, so our rate is 0.0033 or 0.33%. Okay, so 4 significant figures. Now, in these questions where they say to 2 decimal places, work to 2 decimal places. Otherwise, what you'll find is your answer comes out €1 or €2 short of the answer at the back of the book, and it's just a bit of a pain when you're correcting. You're never sure if you've done it right or if it's just a decimal error. So we'll work to 2 places of decimals there. The other thing that's important is the day she makes the deposits here. So she's depositing on her 18th birthday, and then the month after and the month after, which is the difference of, were she to make her first deposit a month after her 18th birthday, at the end of each month instead of the start of each month, it would change the calculation. Now, between her 18th and 21st birthday, that's 3 years, but we're talking about monthly deposits, so that's 36 months. So the first €30 she puts in there earns a monthly interest rate of 0.33%. So you multiply by 1.0033 to increase it. But that first deposit that she puts in on her 18th birthday, that's going to sit there for the whole 36 months. Then a month later, she puts in another €30. Okay, well, that's only going to sit there, earning that same 0.33%, but it's only going to sit there for 35 months. So the future value of this €30 is different to the future value of the first €30. And that's going to be true of the next one and the next one and the next one, until eventually the last deposit she makes is a month before her 31st birthday, or 21st, and that's going to sit there for 1 month. The deposit she made before that sat there for 2 months, and so on. Okay, so how many deposits do you have? Well, 1, 2, 3, 4, 5, 6. You've got 36 deposits. What does that set of numbers represent? Well, that is a geometric series. And if I didn't hint enough when we were studying geometric series that it was going to be very important for financial maths, let me say now that it is. This is our formula for the sum of a geometric series. And that's exactly what we want to do. We want to say, well, what happens if we add up all of these terms? What is the sum of all of those terms? Now, it's geometric because if you look at this and call this the first term here, I know it's the last term on the list, but let's call it the first term in our geometric sequence. We're multiplying with each step, we multiply by 1.0033, and so now instead of to the power of 1, it's going to be to the power of 2. And the term before that will have been 30 times 1.0033 to the power of 3. The term before that was to the power of 4, 5, 6, 7, until you get eventually to this final term in our geometric series, which I know is the first deposit she made, so you do have to kind of invert it. But what do we have? Well, our first term is 30 times 1.0033. Our common ratio, we're multiplying by 1.0033 with each step. And our number of terms is 1, 2, 3, 4, 5, 6. It's 36 terms. So using our formula, which you've seen before for geometric series and is in the log tables, we're going to come along and say, well, A, that's 30 times 1.0033 multiplied by 1 minus the common ratio, 1 minus 1.0033 to the power of n for us is 36, all divided by 1 minus the common ratio, 0.0033. Okay, and because I have the calculator work done on this already, I know that that answer comes out as 1,148 euros and 55 cents. Okay, I suppose it's kind of interesting to look at the equivalent. If you just said, well, 36 months, if you'd stuffed that 30 euros under a mattress for 36 months, you would have come out with 1,080 euros. So you're making yourself 68 euros and 55 cents there off the interest, which isn't bad. Now, these things really take off when you're saving over a longer period than 3 years, though. Question 4 asks you to show that the final value of a series of payments, just like Marie was making here, she was making 30 euros payments, we're making payments of size P, earning an interest rate I, okay, so she had an interest rate of 0.33, you've got an interest rate I, can be written as this here. Okay, well, let's have a look. First payment is P, sits in the bank account earning, well, you increase it by I% each month. Okay, so, or each year, I think is what this question is saying, per annum. Okay, so after n years, it's been sitting there for n years, that's the future value of your first payment that you make. But of course, 1 year later, you come along and you make another payment, but that doesn't sit there for as long. Okay, if that was 20 years, this is 19 years. If that was 30, this is 29. If that's n, this is n minus 1 years that one sits there for. And that goes on really until you get to your last payment, which is going to sit there for just 1 year. Okay, and you're making your payments here at the start of each year, and that's important. Okay, I'll discuss that with question 8, the importance of that timing, but just trust me for the moment. You make the payment at the start of the year, so this is at the end of the year we're evaluating it. We're saying, well, it's earned 1 year's interest. Okay, well, that again is our geometric series. Our first term is given by this, P times 1 plus I, our common ratio. Maybe I should have included the previous term to that, which would have been P times 1 plus I squared plus, that's the last term then. Okay, so you're multiplying to get from here to here by 1 plus I. So our common ratio is 1 plus I. And our number of terms in this case, well, it's just n. So they've asked us to come up with a formula. Well, the sum of all of these things is a times 1 minus r to the n all over 1 minus r. Well, a here is p times 1 plus I times 1 minus, the common ratio is 1 plus I to the power of n, all divided by 1 minus 1 plus I. Now, that looks similar to what they've asked us for, actually. If you look here at question 4, you got the p times 1 plus I. Yeah, you've got 1 plus I to the n, but it seems to be in the wrong place. And you just have an I in the bottom, and you've got a minus 1. Okay, well, where does that come from? If you look at the bottom here, you get 1 take away 1. That's 0. And then you just got minus I in the bottom. So that's p times 1 plus I over 1 minus 1 plus I to the n over negative I. Okay, and we don't like to leave negatives in the bottom of fractions, so I'm going to multiply top and bottom here by minus 1. And what I get is p times 1 plus I times, well, 1 times minus 1 is minus 1. Minus 1 plus I to the n becomes plus 1 plus I to the n, all divided by I. And that's the formula they've asked you to get there in question 4. We don't really use that formula very often. I prefer you to learn to use the geometric series and use this formula here. Okay, that's the one that I'm going to come back to over and over. And the Leaving Cert really likes to ask questions about that formula. So do make sure you know it, and make sure you know how to do a savings question using that formula. Okay, I'll wrap up here with question 8, which is just working backwards, I suppose. George wants to make regular payments of some amount. Okay, now down here it says he's investing at the beginning of each year. Again, that thing with timing is important. I've actually included up here. It's at the start of each year he's making the payment into an account that pays 8.5% each year, compound interest, and he wants to have 10,000 euros at the end of 7 years. Find how much he must invest at the beginning of each year. Okay, so I've actually written this one out in its all 7 terms, just because 7 is a small enough number. It's not like 36 that we had in question 2, where you're not going to write out 36 terms. So there's the amount he has to invest each year. Okay, at the start of year 1 he invests some amount A. That sits in the account earning 8.5% for 7 years. Okay, then at the beginning of the second year he invests that same amount again, but that only sits in the account for 6 years. At the beginning of the third year he puts A into the account, but that ends up only sitting in the account for 5 years. Okay, and so on until finally at the beginning of the 7th year he puts A into the account, and that sits there for 1 year until the end of the 7th year, and he needs all that to add up to 10,000 euros. Okay, well, again we've got our geometric series. If you look here, you're multiplying with each step, you're multiplying by 1.085. Okay, and because you're multiplying by the same amount with each step, that is a geometric series. Just working backwards. So there's our first term. There's A in our geometric series. That's lowercase a, I suppose. Our first term, which is uppercase A. I should have used a different variable there. Sorry about that. Uppercase A times 1.085. Our common ratio, we're multiplying by 1.085. And the number of terms is 1, 2, 3, 4, 5, 6, 7. No surprises there. 7 years, 7 terms. Now, we need that all to add up to 10,000 euros. So the sum of this geometric series needs to be 10,000 euros. And we know our formula for the sum of a geometric series is A times 1 minus r to the n, all over 1 minus r. Okay. So we need our sum of our geometric series, which is A times, A is, lowercase a is this whole thing, capital A times 1.085. That's the amount he invests multiplied by his interest rate, times 1 minus r, 1.085 to the power of n for us is 7, all divided by 1 minus 1.085. And we need that to add up to that 10,000 euros, which is what he wants. Okay, now, if you just go to a calculator and work out that figure there, you find that is A multiplied by, and I have it here, 9.83 needs to equal 10,000 euros. And then dividing across 10,000 euros divided by 9.83, that'll give you 1,017 euros and 23 cents. Okay, so that's how much he needs to invest every year in order to have 10,000 euros at the end. Now, 8.5% is an astronomical interest rate. If the bank ever offers you that, absolutely take it, or examine how legit your bank is. If you take that 1017 0.23. If he was just stuffing that under a mattress every year, he just multiplied by 7 and he'd come out with 7,120. So you can see there's nearly a 3,000 euros, 2,880 euro difference between saving on a regular basis with interest or not saving. I'll finish up by addressing this thing. What if you've been saving this money at the end of each year? Well, then really this first amount would have landed in on the day he was taking money out, so we wouldn't get any interest on that. This would have only sat there for 1 year. This would have sat there for 2. This would have sat for 3, 4, 5. And the first amount he would have paid, because he waited till the end of the first year, it really would have only sat there for 6 years. So you still have 7 terms. You still have a common ratio of 1.085, but your first term A is just whatever he's investing. So you don't get this extra, I suppose, boost of having a bigger first term. So that number is going to come out smaller. So he's going to have to invest slightly more each year. Okay, I'll assign questions in the email.